This is a Microsoft briefing on the use of switched virtual circuits on DSL networks. For further information, please check the URL provided at the end of this presentation.
Welcome to the Microsoft demonstration of switched virtual circuit technology for DSL, usually referred to as SVCs. We hope this brief presentation will help to highlight the consumer and operations cost benefits of using SVCs for your DSL deployment. This demonstration will show you why we think SVCs are an important capability for a broadband service. Here we have a regular home computer attached to a DSL modem. In this case, we're using an ATM25 connection to the modem, but it won't be long before the modem moves inside the PC as an internal card or is attached using a USB connector. In either case, the modem will appear to the operating system as an ATM device, exactly as we're seeing today.
At the central office, the DSL link terminates in a DSLAM, that's DSL Access Multiplexer. In this cabinet, we have consolidated the services of Telco, ISP, Enterprise RAS, and Broadband Media. For this demonstration, we are using a prototype of the Fujitsu SpeedPort DSL system, which supports ATM SVC switching on the DSLAM itself. The DSLAM aggregates the ADSL traffic and multiplexes onto one or more ATM fiber links. In this case, an OC3 SONET fiber to the ATM network. We're using the 4 ATM switch as our ATM network for today, with signaling running between the client, the DSLAMs, the switch, and the servers. To act as our service providers on our network, we have 3 small Windows 2000 servers. One acts as an ISP, giving us authenticated IP access to the internet and hosting our web pages. The other behaves like an enterprise RAS server, and the third will provide streaming media. You will see these in action later on. Remember, we don't have any permanent virtual circuits to manage here. All connections are configured automatically as SVCs.
Now let's go through the process of setting up an internet connection from the client. We're using Windows 98 2nd edition for this. First, the user opens the browser. Dial-up networking signals to the DSLAM for a connection, giving the ATM address of the service provider. The address has previously been supplied to the client PC, perhaps as a pre-configured icon, or as part of a service installation or sign-up process. The DSLAM routes the call to the ATM network, which delivers it to the server. The server accepts the call, and the ATM connection is established. Now, dial-up networking starts up a PPP session. It submits the user's login name and password for authentication. The server checks these against the ISP's membership system. When accepted, the server passes back an IP address and DNS addresses to use, as for any dial-up connection. With an IP address and known DNS server addresses, the browser can now use TCP/IP to request the web page the user asked for. Now let's see Jeff do that on the network.
Sure, Mark.
Pretty quick. Now that we're connected, we can browse around to other websites with full broadband speed. You see, an SVC system may not be always on like a PVC, but it is certainly always available. And for most users, there really isn't any difference in experience. However, with SVCs, I don't always have to go to the same place, and I don't have to be charged for connections I'm not using. Now imagine that my corporation has also connected to the ATM network to allow broadband telecommuting. The connection procedure is the same as we did for the ISP before. So let's place a call to a corporation. I close the current ISP connection and launch one to my company. Again, the company IT department would have provided the icon and ATM address when they set me up. Now, instead of being logged on to the public internet, I'm connected directly to my company network. This is not a tunnel or VPN, it's a directly dialed ATM connection, much like dialing in with a modem today. The big cost advantage here is that the corporation doesn't have to pay for a huge analog modem rack, nor do they have to buy a fat pipe from an ISP for tunneling. A single Windows 2000 server can handle perhaps 1,000 telecommuters or more on a single ATM link. Jeff will now show you a couple of multimedia examples.
Thanks, Mark. We've shown how an SVC can be created when required and go where the user needs it to go. There's a third important reason to deploy SVCs. For some applications, a best effort connection simply isn't good enough. Examples are voice and video connections. Let's take a look at an example of this. First, we use our default connection to the ISP as we did before to get a regular web page. But now we want to use a web page with content specially designed for broadband environment. Now we click on the link. We're still using the dial-up networking connection for our DNS and basic web pages, but the software is set up to use an additional SVC direct from the media server for streaming purposes. This means that the video doesn't have to mix with internet traffic or even go through the PPP protocol stack. Let me show you what I mean. As you can see, we now have 3 active connections. One of these is our original SVC to the ISP. The other 2 go to an ATM ARP Mars server for an ATM address resolution, and go to the media server to carry the movie streams in a more efficient long packet format. This allows us to stream full-screen video or any other value-added content, so a broadband ISP can offer media-rich, highly differentiated services to users and advertisers.
The ATM network can give guaranteed quality of service for the duration of the connection and take back the resources when the user has finished with them. The user can also sign up for additional or replacement ISPs without requiring manual intervention by the telco. This can provide significant savings for the telco operational costs. An ISP can now build a walled garden of high-value services using media servers attached to the ATM network, offering a much richer experience for users and advertisers alike. Enterprises can now extend multimedia voice and video services out to telecommuting employees and customers.
Finally, if we have ATM to the first computer in the home, what do we do about other computers on a home network? The short answer is to use Windows 98 Internet Connection Sharing. In this case, we have a simple Ethernet link between our 2 PCs. We have ICS installed on our DSL computer, and the other computer uses DHCP to find out about the network as it would on any other LAN. With ICS installed, other users in the home can share the connection to the ISP and browse the same as if they were on a LAN in an office. Internet connection sharing handles all the address allocation and translation required. If the ISP connection isn't already in place, ICS can be set to dial it automatically, giving every user the always available experience. It can even handle PPTP tunnels, voice and video calls, and many of the newer multiplayer games. In this short demonstration, we've shown that the flexibility of an SVC architecture is easy for the user to understand and provides powerful opportunities for ISPs and DSL networks to differentiate themselves in a competitive environment. Microsoft is continuing to promote the switched virtual circuit as a key part of the future-proof broadband strategy for DSL. As such, we are including all of the SVC support you saw today in Windows 98 2nd Edition and in Windows 2000. There are many other advantages to an ATM SVC architecture, including the support for incoming calls to the home and the provision of voice services over the data path. But we hope this short presentation has given you an insight into the real end-user benefits of this approach to DSL networking.
For further information on DSL networking and the use of SVCs, please check out the URL on your screen. Thanks for watching.